Welcome back. Today we explore light, shadows, and reflections. Imagine the golden sunrise painting the coasts of Odisha. Light is what wakes up the world. But what is light? It's a form of energy, electromagnetic waves that our eyes can detect. Without it, we would be in pitch darkness. We categorize objects by their relationship with light. First, we have luminous objects. These are the light emitters, like our sun, generating massive energy. It's not just stars. Nature has its own lanterns, like fireflies using bioluminescence to glow on a quiet Diwali night. Then we have non-luminous objects. The moon, for instance, seems to shine, but it's actually just a rock reflecting the sun's brilliance. Now let's look at how materials interact with this light. We classify them as transparent, translucent, and opaque. Transparent materials act as open gates. Clear glass, air, or pure water allow light to pass through completely, giving us a perfect view. In these materials, light rays travel in straight lines without getting scattered, which is why the image on the other side is crisp and clear. Next is translucent. Think of frosted glass, tracing paper, or even a heavy morning fog. Light passes through, but it gets scattered. Because the light is diffused, you can see a glow, but you can't see a sharp image. It's like looking through a veil. Finally, opaque materials. Cardboard, wood, metal, or stone. These are the gatekeepers that say, "Stop" to light. Since light cannot pass through them, it is either absorbed or reflected back, creating a dark region behind the object, a shadow. Let's put this to the test with a simple experiment. Imagine shining a bright torch through different objects in a dark room. If you shine it at a glass pane, the beam punches right through, creating a bright spot on the wall behind. That's transparency. Shine it through a tissue or oiled paper, and the object itself glows with diffused light, but the wall behind sees only a soft blur. But shine it at a book, the light stops dead. A sharp, dark shadow appears. This simple test classifies our world. We use these properties every day. We choose transparent glass for windows to see out, but translucent glass for bathrooms for privacy. In culture too, Diwali lanterns are transparent to beam hope, while the opaque clay of the diyas shapes the beautiful shadows of the night. Think of the massive opaque chariots of the Rath Yatra, blocking the sun to cast giant, cooling shadows on the devotees below. Light is fascinating. It defines what we see, what we hide, and how we celebrate. I challenge you to find 10 examples of each material in your home today. Light isn't just magic mist. It zips precisely. It travels at a staggering speed of 3 × 10 to the power of 8 meters per second in a vacuum. A fundamental property of light is its path of travel, rectilinear propagation. This simply means light travels in a straight line. Rays are just models of these paths. Think of the Odisha Rath Yatra festival. The straight torch beams piercing through the night crowds? That's rectilinear propagation in action. Why straight? It's about the wave nature. Rays are perpendicular to wavefronts. According to Huygens' principle, each point acts as a source, creating a straight net path. Let's prove this with experiment 1. The 3 matchboxes. Take 3 cardboard boxes and prick a pinhole in the center of each. Stack them perfectly straight. Shine a torch at one end. If the holes are aligned, the light spot is visible at the other end. The light zips through the straight tunnel. Now, shift the middle box by just 1 centimeter. What happens? It goes dark. The misalignment blocks the path because light cannot bend around the cardboard. Experiment 2, the bent pipe. Take a 30 centimeter straight PVC pipe. Look at a candle flame through it. It's clearly visible, right? Now, add a 90-degree elbow joint. Look again. Nothing. The flame disappears. The light hits the bend and stops. It doesn't curve like water in a hose. Mathematically, the tolerance is tiny. With a 2 mm hole and 10 cm distance, a misalignment of just 1 mm creates an angle that blocks the view. Real-world proofs are everywhere. Look at sharp shadows at noon. The sun acts as a point source, and opaque objects block the straight rays, creating an umbra. Pinhole cameras rely entirely on this. They project an inverted image because light rays from the top travel straight to the bottom, and vice versa. What about seeing around corners? We use periscopes. But even there, light travels straight. It just bounces off mirrors. It never curves. In Odisha, the Konark Sun Temple is a marvel of this physics. The wheels and pinholes align perfectly with sunbeams during solstices. Even during Deepavali, when we make rangoli, notice how laser pointers trace straight lines across the floor. Light paths are precise geometric lines. Are there exceptions? Well, advanced physics tells us about refraction, where light bends when changing mediums, like a pool looking shallow, or diffraction, where light curves around tiny edges. But for our matchboxes and pipes, the straight line rule holds firm. So, whether it's a bent pipe or a temple design, remember, light zips straight. This phase builds our foundation for understanding mirrors and lenses next.
Welcome back to our study of light. In phase 2, we learned light travels in straight lines. Now in phase 3, we see what happens when those straight rays meet a blocker. We get shadows. A shadow is the dark side of light. It forms when an opaque object intercepts the path of light, creating a zone where no rays can reach. We call the requirements the Holy Trinity of shadows. You need 3 things: a luminous source, an opaque object, and a screen to capture the shadow. If any one of these is missing, you won't see a shadow. No source means darkness. No object means a lit screen. And without a screen, the shadow is invisible in the air. With extended sources like the sun or a bulb, shadows get complex. You get a dark center called the umbra and a fuzzy outer ring called the penumbra. A perfect example is the 2023 annular eclipse seen in Odisha. The moon acted as the opaque object, blocking the sun's light from reaching the screen of Earth. Here's a key rule: shadows are always dark, regardless of the object's color. A red apple blocks red light just as a green book blocks green light. The shadow is always black. Shadow size depends on geometry. If you bring the light source close to the object, the rays diverge widely, creating a giant shadow. Conversely, if the object is near the screen, the shadow is small. And for distant sources like the sun, the rays are nearly parallel, so the shadow is the same size as the object. For the math lovers, we can use similar triangles. The ratio of the shadow's height to the object's height roughly equals the ratio of their distances from the source. You can prove this in your shadow lab. Take a torch and a stick. Measure how the shadow shrinks as you move the stick closer to the wall. It's geometry in action. Also, try using a translucent object like tissue paper. You won't get a pitch black shadow, just a fuzzy, faint patch because some light still passes through. Shadows aren't just for science, they're art too. In Odisha's Patachitra and traditional Tholu Bomalata, artists use light and opaque puppets to tell stories. These intricate puppets act as the opaque blockers, and the screen brings the epic tales to life using the simple principles of rectilinear propagation. We also use shadows to tell time. Sundials track the changing angle of the sun by the length and position of the shadow cast by the gnomon. Remember, the sharpness depends on the source size. A large bulb makes a fuzzy shadow, while a laser point makes a crisp, sharp one. A crucial safety warning: observing shadows is safe, but looking at the source isn't. Never look directly at a solar eclipse. Use a pinhole screen instead. Here is a challenge for you. Go out to the school ground at different times of the day. Measure your shadow length. Can you calculate the sun's angle? So, from simple hand puppets to cosmic eclipses, shadows are everywhere. They are the dark proofs that light travels straight. Thanks for watching Phase 3. Welcome back to Phase 4. We've talked about light sources and shadows. Now we're diving into the shiny magic of mirrors and how they flip our reality. Reflection is simply light bouncing off a surface. If the surface is smooth, like a mirror, we get a clear image. This is specular reflection. Rough surfaces scatter light, giving us diffuse reflection. The law governing this is strict. The angle of incidence always equals the angle of reflection. And remember, the incident ray, reflected ray, and the normal all lie on the same plane. Historically, we've used polished surfaces for ages, like the Odisha brass mirrors or kavacha, which were polished to perfection to create reflections for rituals. Now, look at a standard plain mirror. It acts like a virtual wardrobe. The image formed isn't real, it's virtual, meaning it appears to be behind the mirror. One key property is size. The image height is exactly equal to the object height. The mirror doesn't magnify or shrink you, it shows a true to size reflection. Also, the distance is preserved. If you stand 10 centimeters in front of the mirror, your image appears 10 centimeters behind it. We can prove this with simple pin experiments. But here is the trickiest part: lateral inversion. Your image is upright. It's not upside down, but it is swapped left to right. This is why ambulance is written backward on the front of emergency vehicles. When you see it in your rearview mirror, the reflection flips it back so you can read it instantly. Why do we call it a virtual image? Because the light rays don't actually meet behind the mirror. Your eyes just trace the diverging rays backward, tricking your brain into seeing an image there. You can't catch a virtual image on a screen. If you put a paper behind the mirror, nothing projects onto it. It exists only in your line of sight. Things get even crazier with multiple mirrors. 2 parallel mirrors create an infinite tunnel of reflections. 3 mirrors at right angles, you get 6 images. We use this in periscopes too. 2 mirrors reflect light around corners, allowing us to see over walls or from submarines without being seen. Mirrors are crucial for safety. While plain mirrors are true to size, cars often use curved convex mirrors to give a wider field of view. But we'll cover that later. Try this at home. Touch a mirror with your fingertip. If there's no gap between your finger and its reflection, it's a surface mirror. If there's a gap, the reflective layer is behind glass. Fun fact, your brain is constantly correcting for these flips. It ignores the inversion so well that you might not even realize it until you try to read text in a mirror. That's it for Phase 4. We've mastered the plane mirror. Next time, we'll bend reality with curved mirrors. Try designing your own backward shop sign tonight.
Welcome back to Phase 5, Optical Devices. In our previous phases, we mastered light properties, shadows, and reflections. Now, we're taking those straight rays and turning them into real-world wizardry. No batteries required, just pure optics. Let's start with the pinhole camera. It's essentially a lensless projector. Because light travels in straight lines, rays from the top of an object pass through the pinhole to the bottom of the screen, creating an inverted or upside-down image. You can build this yourself. Take a shoebox and paint the inside black. Poke a tiny pinhole in an aluminum foil center on one end and use a wax paper screen on the other. It's affordable science. Odisha kids craft these from shoeboxes for science festivals. The science is precise. Magnification equals the screen distance divided by the object distance. Also, brightness depends on the hole size. But a critical warning, never look directly at the sun through a pinhole. Only view the projected image to stay safe. This isn't new tech. Ibn al-Haytham studied this back in 1015, marking the birth of optics. Artists later used camera obscuras to trace reality perfectly before photography existed. Next, the periscope. It's the obstacle spyglass. By using 2 mirrors set at 45-degree angles, we reflect light twice. The first mirror turns light 90 degrees down, and the second turns it 90 degrees to your eye, giving you an erect image over walls. This mechanism changed history, from trench warfare to submarines lurking beneath the waves. But it's also fun. You can build one with a cardboard tube and 2 small mirrors to peek over crowds at festivals like the Rath Yatra. Now for the kaleidoscope, a symmetry symphony. Here, we place 3 mirrors in a triangle. The objects inside reflect back and forth, creating 6 or even 12 images from a single bead. It's infinite variety from simple reflection. To build one, take a 20 cm PVC pipe and slide in 3 mirrors to form a triangle. Add some colored beads or glass bits at the end. Spin it, and you get mandala madness, a principle used in traditional Odisha crafts. Let's compare. Pinhole uses rectilinear propagation for an inverted image. Periscope uses double reflection to see around corners. Kaleidoscope uses multiple reflections for symmetric patterns. All simple, all powerful. These ancient principles power our modern world, from pinhole roots in cinema projectors to periscope mirrors evolving into fiber optic endoscopes for life-saving surgery. The past illuminates the future. Here is your challenge. Can you combine them? Try building a hybrid kaleido-periscope. Use these timeless toys to explore the science of light. Stay curious, and see you in the next phase.
Welcome back to class. Today, we are going to go through the detailed solutions for the Let Us Enhance Our Learning section of your textbook. We'll explore light, shadows, and reflections. Let's start with question 1. Which objects are luminous? The correct answer is the sun and the pole star. Why? Because luminous objects generate and emit their own light energy. On the other hand, Mars, the Moon, Venus, and mirrors are non-luminous. They simply reflect light from other sources. Question 2 asks us to match the columns. Let's break it down. A pinhole camera is known for forming an inverted image. An opaque object blocks light completely. A transparent object allows light to pass through almost completely. And finally, a shadow is defined as the dark region formed behind an opaque object. Moving to question 3. Who can see the candle flame? The answer is Rekha. This demonstrates a fundamental property of light. It travels in a straight line. Since Rekha is using a straight pipe aligned with the flame, the light reaches her eye. The others, using bent pipes, block the path of the light. Question 4 is about shadow formation. The correct image is A. Remember the rule. Shadows are always formed in the direction opposite to the light source. With the sun behind the boy, his body blocks the light, casting a shadow on the ground in front of him. Questions 5 and 6 deal with the size of shadows. Option A is correct. Here is the logic. If an object like a ball is moved closer to the light source, it blocks a larger angle of light, creating a larger shadow. Conversely, moving the light source away makes the shadow smaller. For question 7, you need to sketch the image of a tree in a pinhole camera. The key detail to get right is the orientation. The image must be inverted, that means upside down, compared to the actual tree. Question 8 explores mirror writing. When you hold your name to a mirror, it appears laterally inverted. This is a fancy way of saying reflected. Left becomes right and right becomes left. It's the same reason why ambulance is written backwards on emergency vehicles. Question 9 asks, when is your shadow shortest? The answer is 12 p.m. or noon. At this time, the sun is at its highest point, directly overhead. Light falls vertically, meaning very little area is blocked by your body on the ground. Question 10 is a tricky one about the letters T and O. Both statements are actually true. While mirrors do laterally invert everything, these specific letters have vertical symmetry. Flip a T horizontally and it still looks like a T. That's why they appear unchanged. Question 11. Can a Z-shaped tube be a periscope? Yes, absolutely. The secret lies in the mirrors. You place 2 mirrors at the bends, angled at 45 degrees. Light hits the top mirror, reflects down the tube, hits the bottom mirror, and reflects straight into your eye. Finally, question 12. Why don't we see a high-flying bird's shadow? It's about distance to the screen. When the bird is high, the shadow spreads out and becomes too faint to see before reaching the ground. It only becomes sharp and visible when the bird flies low. That concludes our solution session.